All right, section 7.2 is going to go into detail about one specific sampling distribution. That would be the sampling distribution of sample proportions. And then just, as a heads up, 7.3 is going to deal with the sampling distribution of sample means. So these are the two most common statistics in the world, I guess. People talk about, presidential candidates' approval rating, that's a proportion, or they talk about the average income. These are the two most popular statistics. So they're the sampling distributions we're going to look at. So first, let's just explore this applet, kind of a simulation of sorts. So what this is a little Reese's Pieces candy machine where the percentage, there's in this infinite population, there's 50% are orange. We're going to sample 25 candies. We're going to take one sample, and then what it's going to do is it's going to take a sample of candies and it's going to calculate the percentage of the candies that are orange, or the proportion of candies that are orange. So let's go ahead and do it once. So we got 48%. It plots that point down here. So this point represents a sample proportion from a sample size of 25. And I can draw another one. So the true proportion is 50%. So we would expect this to be 50%, but for some reason we're getting 44% and 42%. That would be random chance variability, right? So let's take a whole bunch of samples. We can take like 100 samples at a time. If I can get my keyboard to work. Come on. Now we don't want to animate because we don't want it to draw 100 of them in a row. So I think it kind of just does one. And here's a kind of a picture of the sampling distributions. Right now I got 102. I can kind of keep drawing them. We kind of get this distribution here. So this is a picture of the sampling distribution of sample proportions. It looks like it's centered at about 50%, which is exactly what we'd expect, right? That tells us that our sample proportions are an unbiased estimator of our population proportion. And then you can kind of see the shape. And first of all, I want you to kind of see that these are approximately normal. Now, what's working against normality here are these spikes to it. We got these gaps and these spikes. So that's kind of why we would say maybe it's not approximately normal. But it looks like it's symmetric. So what happens if we sample 100 candies? By the way, our average spread is about, right now is 50% to about, on average, maybe 62. So we got about a 12% spread here on average. So if we do 100 candies, again, if I wanted to do one, I guess I could do one just to show you what it looks like. So now we're going to pick 100 candies. Looks like we're getting a lot of oranges. Looks like we're going to be over 50%. Or I guess this one's wider, so it's hard to tell, I guess. Who knows? I shouldn't have done 100. Okay, 53%, so I guess we're over half. So let's just do 100 of those. Take the animation off and see what those look like. So as you can see, when our sample size is a little larger, we have less of the gaps, less of that discrete nature. This looks like it's approximately normal. Like a normal curve would approximate it pretty well. Still looks like we're unbiased, but now it looks like our average spread is about maybe 6%. As our sample size increases, our variability decreases. So we talked more about this in class. We talked about, if you look at the number of oranges, how it's kind of like a binomial distribution. And we even kind of linked, if you remember when we could use a normal approximation for a binomial model. It was called the large counts condition. Well, if you divide by n and get you percentages, it's kind of the exact same thing. So this distribution is going to be approximately normal if the large counts condition is satisfied. Like I said, we talked a little bit more about it in class, but that's kind of the gist of it. I will point out to you, though, that if we're at 100, if we have a really small proportion, like 0.02, and we draw our samples, notice our distribution is not normal, it looks like it's skewed to the right, and it's kind of got that discrete nature. And if we kick this up to 200, I think we're still going to kind of observe the same type of thing. Just got a little bit of skewness to it, it looks like. So the thing that tells us whether these are approximately normal is the large counts condition. I guess that's all I'm going to mention on the video here. So let's talk about, let's describe these distributions. Let's go back to the 50% here. And we'll take, I guess we'll take 200, that's fine. Okay, so we want to describe this distribution. We want to describe the center, we want to describe the standard deviation, and we want to describe the shape. So let's do this in the notes. If you take a simple random sample, so this is the condition that's important here. In fact, I think I highlighted this. If you take a good random sample, that's the condition that is important on this one. Then your p hat is an unbiased estimator of p. In other words, the mean, why am I writing it? The mean of my p hats is equal to the true population proportion. It's unbiased. It's centered right. But you got to take a good random sample. If you just go ask, you know, like if we're talking about approval ratings of the president, if you go ask your Democrat friends or your Republican friends, and you know, then it's going to be biased. It's going to be off-center. But if you take a random sample, it should be centered properly. Spread. So this is the formula for the spread. Now, I did derive this in class, and I did talk about it, how it comes from the binomial model. But you're not really responsible for that, so I'm not going to really mention that here in the video. But if you pass the 10% condition, so you can use this formula if the condition is if you have independence. The proof of this formula, when we did the binomial model, we needed independence. We never have independence with the if we're sampling without replacement, we don't have independence. But as long as the 10% condition is satisfied, we have pseudo-independence. That means this formula is going to be good enough. And if you're wondering how good is it or why is it the 10% condition, do that BAPS worksheet, that worksheet that talked about what you do whenever the finite population correction or whatever it was. But you don't need to worry about it. That's it. Just plug it into the formula. We got PQ divided by N, take the square root of it. Let's talk a little bit about what happens when the 10% condition isn't satisfied. And as I mentioned in class, this formula, let's say this formula gives us well, actually, let's actually calculate the formula. Let me pause the video for a second here. So I just want to do a quick little demonstration of that to show you that this formula works. For this applet, when 50% of the candies were orange, we had a sample size of 200 to kind of give us this shape. Now, if we could, I can't draw on top of this, but if I could draw a normal curve to kind of approximate this, and then go from the center to the point of inflection, I would say that it looks like this standard deviation is maybe about, I don't know, kind of looks like maybe 3 percentage points, 4 percentage points, 4.5, 5, I don't know. But we can actually calculate that using this formula. Just plug in our values. So the proportion, true proportion is 0.5. That's probability of success, and then Q would be 0.5 as well, 1 minus P. And we have a sample size of 200. If I hit Control Enter, you can see it gives me a standard deviation of about 3.5. That looks like the standard deviation of the sampling distribution. So it kind of works. Now, if this formula gives us 3.5 percentage points for our average error in our approximation, then what happens if the 10% condition fails? So if the 10% condition fails, the only thing I mentioned in class was that this formula is not accurate, so this is not a good estimate. But what I want to point out to you is that if you are sampling larger than 10% of the population, then your actual standard deviation is actually smaller than this. Meaning, if you got 500 people in the population and you survey 450 of them, because you're taking such a high percentage of the population, the spread of your statistic is actually going to be much smaller than this formula predicts. That's actually a good thing. That means your estimates are better than you would think. So it's not actually a bad thing to fail the 10% condition. It's just, if you fail the 10% condition, this is not going to be a good estimate. We'll just leave it at that. Shape. The shape's going to be approximately normal as large as the large counts condition passes. So that's the condition for this one, large counts. So each of these aspects of the distribution has a condition that kind of goes with it. N times p greater than or equal to 10, n times q greater than or equal to 10, just like the binomial distribution when we were using a normal thing to approximate it. Okay? So this is just a summary of it, saying kind of the same thing. We don't have to go over it again. So we've got an example here. I think we should probably stop the video and start a new one. Actually, this is the last. Ooh, we do it in 4 minutes? Yeah, let's try to get it done. So suppose, the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a 4-year. I'm not going to hurry it. I'm sorry. Next video.